Hey.
thanks, Aaron. Yeah, and yeah. So as you were saying, I mean, I'm focused on energy transition. I've worked around the world, but always been based in primarily based in Canada, and coming to you from Victoria, British Columbia today. I'm going to describe the state of battery energy storage in Canada very briefly at a high level, and then discuss some of the ways in which we envision that battery energy storage systems contribute to climate resiliency, and then any exposure that they have to climate change. And so we're kind of attacking it from two different directions. Yeah, so I will kick us off. Um, where I'm just going to give you a very brief Charge Solar interview or overview so that you understand the context of how our company is involved in Canada with battery energy storage systems. I'm going to give you a feeling for the size range. I'm focused today on grid-tied storage systems. And so from very small residential systems at homes that are already connected to the grid all the way up to the largest scale deployed in Canada today. And I will recap the applications. And so while the climate resiliency is kind of the primary topic that Aaron asked me to cover today, I realized that a lot of people on the call may also be wondering what the sizes are and what these batteries are being used for, because it really sets up the context for climate resiliency. So, very briefly, Charge Solar is a national company selling solar and battery systems to residential and commercial installers across Canada. So, we're really enabling them with what are the products that are globally available, what's best suited for Canada, certified for Canada, and then coupling the equipment sales with engineering services. We're serving the resi, industrial, commercial markets primarily. We still do a little bit of RV stuff, but a lot of that's been commoditized through big box stores and some of the uh, online e-commerce stores that people can do DIY work on. So we're primarily in resi and commercial and industrial across the country. We have a full range of solar modules, but also all the inverters that make, grid ready power. And then, of course, increasingly batteries, as well as a range of solar mounting options, whether it's mounting to a roof or the ground or top of pole mount in some cases. Uh, and just briefly, I'll mention, because I know there'll be a lot of technical folks on the call. We're providing engineering services to the installers to then help their end customers, again, at a resi or commercial level. But we're also heavily involved in standards development. And I'm going to reference a couple of standards later in the session today that touch on fire protection, just as one example. So it's really useful, the group on this call, if you have anything to contribute there. Let's say you're working on climate resiliency and you might have some comments or questions on batteries. Hopefully, we get into that in the Q&A. Let us know, because we can bring those back to technical advisory committees that are focused on evolving these standards as well in Canada. It's still very new and evolving and changing all the time. And so we're regularly contributing on that front. Okay, let's jump right into battery energy storage system overview. Again, I'm defining the scope here to not include for the moment. I'm going to talk stationary storage, and I'm going to stick to lithium ion battery storage. So not flooded lead acid, which is still used in some remote cabin applications in Canada. And I'm not getting into any non lithium ion chemistries, of which there are increasing quantity. On the very small end of grid-tied battery energy storage systems, this is my garage, just for full disclosure, and I've got two 5 kilowatt hour batteries, very small. Again, I know we're going to have a wide range of people on the call, so just say briefly, 10 kilowatt hours total in a home can allow all of your critical loads to run for a full day. And then if you have a solar solution, then you can usually on a smaller set of loads, you could run indefinitely with solar recharging the batteries during the day and then powering critical loads at night. If you wanted to have a full whole home, all of your loads on all the time, depending on the nature of your heat source and a variety of other things in the home, you'd need quite a bit more storage. But this is really just for several hour outages and or longer term outage protection when you're going to curtail quite a few of the loads in the home. So just to give you a feeling, that's kind of the small end. Is a lot of resi systems start off at 5 kilowatt hours and kind of go up from there. On the very other end of the spectrum, you have the largest battery energy storage system installation in Canada. This was recently commissioned in Ontario, and you're talking about 120,000 times larger than the example I've got on the left. So You've got 300 megawatts of peaking capacity for the Ontario grid, and it's roughly 4 hours of storage. And so 4 hours of 300 megawatts can make a meaningful contribution. You'll see that it's an array of storage containers, but also you see this interconnection to the high voltage transmission lines that are running along the highway here. And so, substantial infrastructure required, utility scale. Well, I'll get into the applications in a minute here, but this is primarily to support Ontario's grid. So you can see the wide range, and in the middle, what's not shown is, uh, several hundred kilowatt hours or sort of low scale megawatt hour sort of size range for commercial applications. And there's really a lot of growth in Canada on that front. I'll just say as the last point in this slide on the resi front, we used to see about 1 in 50 systems that we're putting solar in, put a battery in. That very quickly is changing to about 1 in 25. So going from 2% attachment rate, as we call it, to about 4% in Canada. In the US, in certain states, it's well over 80%. I mean, in California, virtually every solar system is going in with battery storage for a few different reasons. Canada, we're still in pretty early days, but going from, like I said, about 2% to 4%. But the solar rate is growing as well. And then the rate of those installs that have battery storage is growing for a few reasons I'll discuss. Um, so what are the applications? Some are obvious. So backup is obvious. I already referenced it with my own system, but that could be for a commercial property as well. One of the benefits relative to a diesel generator is there's zero downtime. So these inverters are online, they're tracking the grid. As soon as you lose the grid, there's a transfer switch that flips over, but you don't miss a beat. You don't even see an outage on most of the equipment. It's that quick. And if it's for an application where you need either just a few hours because your grid outages in that region are often not multi-day, or you need for a commercial application maybe just enough energy to wind down some commercial equipment, then backup is one application. And historically, that's about the only application for battery energy storage systems. And then increasingly, it's just a wide array of additional value stacking, as we call it, that you can sort of pile on different use cases. So one of the other applications that we see that's somewhat different to grid tied stuff, and it's sort of microgrid associated, but diesel offset is a big application for us and in some of the projects we're involved in. On the left, you have a remote First Nations village in BC that has a substantial amount of solar that could offset a lot of the diesel generation during the day. Diesel was the only source of energy before the solar was put in. But of course, that's only during the day. And in BC, in particular, in the fall, winter, and spring, there's not a ton of sunlight near the coast in BC. So we put all these solar modules up, but what are you going to do in those shoulder periods in the day and or overnight or all day, all night in the summertime frame? And that is you can't quite see it that well, but there's a little single container in here that is a battery energy storage system that takes all the excess solar from the day, stores it, and then powers the community at night. And so of course, there's a variety of benefits in reducing 90% of the diesel being used at this site. And we were focused on climate change and resiliency. When we got there, it was a lot about just having the audible change and not having the diesels droning on all day and all night. So really great project there. And then on the right-hand side, Experimental Lakes. This is a government research facility in Ontario. Similar kind of application where you're talking about one container. So not the small resi scale and not, massive Tesla entire field kind of installations, but enough that it's going to take excess solar during the day and shift it to be able to be used at night and really tackle local diesel genset issues, which is about local air quality. It's about the cost and logistics to get the diesel into these locations. It's about spills and reduction of the quantity of fuel drops that need to occur. There's just a tremendous quantity of benefits there. And as the cost of stationary storage comes down, it really allows us to put in more solar and get rid of even more diesel. Um, Back to complete sort of grid tied applications. There's a lot of intraday shifting. So, I sort of see a typical generation pattern of solar is very much in the middle of the day for obvious reasons. Quite often, when sized appropriately, solar generation will exceed the load requirement during the day. And again, this is a home or a business, it doesn't matter. But when you have that situation, the very first thing that people will do in most jurisdictions now is charge up their battery as soon as they have an excess of solar generation in the day. And then once the battery is full, which occurs during this hour, they'll start exporting the rest to the grid. There's different value propositions for export across the country. Even in Canada, it's a very sort of disparate landscape in terms of how much value you get for exporting, all the way from zero in some programs in Ontario up to 10 cents, which is what BC is going to move to for their export rate. Yeah, the first thing is uh, time of use rate optimization is sort of one application for intraday shifting. So if you have different import rates during this period of time, then you can lower your import rate from the grid all the way to zero during the middle of the day, which is typically a high rate time of day to be importing. And then you can use the battery, let's say, on a shoulder period of the day when rates might be high, but you don't have high solar generation. So you're sort of using this battery to shift around typically solar generation. TOE rates in Canada aren't that different where a battery alone without solar makes a lot of sense yet. It may in the future where you just have the battery and you're just charging when the rates are low, usually overnight, and then discharging when the rates are high, usually during a morning or an evening peak. So it's usually that these systems are being coupled with solar. So they're putting in a battery storage system with solar. And then secondarily, there's solar self-consumption. It's kind of the same model, but again, I mentioned just briefly in Ontario, there's no benefit to exporting to the grid. And so they'll have a battery in place just to smooth out the solar, regardless of what the rate structure is with the utility. And they'll just smooth it out through the day so that they're importing as little as they can from the grid, and honestly exporting as little as they can as well. So it's almost like you're kind of simulating an off-grid application, even though you have the grid there for redundancy. In solar self-consumption mode, you will, as much as possible, try to be self-reliant on your solar and your battery system. Again, both of these are very common now in Canada at a resi or commercial scale. And finally, you have utility support. Again, those centralized large systems are either bidding into a daily capacity market where capacity, if you're not an electrical person on the call, just means rather than energy, solar is kind of an energy device. It's generating energy at a time that the sun's going to be out. Capacity is another thing that people need to plan for in our systems, which is how much power can you deliver right now? In the next 15 minutes, we need a lot of energy consumption on the grid. The power being delivered is very high. Where are we going to get all that excess power generation from? This is a very recent example, March 29th. In California, they continue to set new records where this big yellow piece is solar generation during the day. So the top line is the amount that the state of California is consuming. And then this is all the different energy sources. And so I know this font's going to be very small, but yellow is the big solar piece in the middle of the day. In most grids, when solar uh, hosting is really drives up above, let's say, 20%, it's this evening peak that becomes very stressful. So the sun's going down, but everyone's also getting home from work and making dinner and having large electrical loads. So if solar, as it closes down to zero here, these other sources historically without batteries would need to ramp at a pace and a magnitude that is too difficult for them to do. So again, I'll just read this out because it's hard to see the text, but the green is wind and this blue is natural gas. And then you have, let's see, you have large hydro and biogas and nuclear is kind of the base generation down here. So only some of those forms are sort of dispatchable and rampable very quickly. And so you have this dispatchable resource that you can deploy geographically around the state where you want and can ramp exceedingly quickly. Those batteries were charged during the day with solar and then shifted to an evening peak to allow load growth in California to reduce the amount of emissions from these other sources that aren't as clean. And this peak right around here of battery capacity that is being provided, again, this is 2 weeks ago, set a new record in California. And it's really exciting to see batteries contributing in a meaningful way that is not experimental. It's not a case study. It's not a test. This is real world, keeping the generation sources, these incumbent sources, from having to grow in the state. Um, this is a daily example. This is happening very regularly. Demand response is less common. So usually utilities will run about 10 to 12 events per year where they're calling on all batteries, resi and commercial, to help them with a grid need. And that could be extreme cold weather, extreme warm weather, but they'll dispatch through a variety of means all of the battery capacity that they can on the grid. Sometimes that's a condition of your interconnection of your battery that they can call upon you as a utility, and sometimes they're incentivizing you to do so on an optional basis. So just here in BC, there's a peak saver program, and you can optionally participate by reducing your load or dispatching a battery and earn additional revenue from BC Hydro. And so again, those programs, unlike the daily capacity market, are 10 or 12 events per year typically, and they're supporting the grid in the most extreme conditions. Okay, so those are the prime. There's other applications, but those are the primary ones that I just wanted to run through, and all very relevant for our Canadian market. Okay, so just move to climate resiliency, and again, we're going to just cover. It's all still relatively introductory in terms of the depth of detail, but we're going to cover how are batteries themselves resilient to events that come from climate change, and then kind of flip that around and say how can they help. So let's start off with some of their exposure. So, you know, I discuss this internally and kind of some of the things we look at, and then there's external standards as well, but they can really be bulked into one of these four categories. I'll talk briefly about seismic under extreme winds, but from a climate change perspective, these are kind of the main four that we wanted to cover, and just say a few words on each of these in terms of how battery energy storage systems are set up to be resilient to these topics. So on the fire front, because there have been, of course, battery fires that are caused by the battery themselves, there's a tremendous amount of research and development that goes on for fire resilience. But in this context, I'm thinking more about forest fires or structure fires that are affecting the battery. So not the battery itself being the cause, but if it's tied up in one of those fires, how can we make sure it's not making things worse, or at least minimize the chance of making it worse? So apologies for all the text on the slide, but I'll just cover these couple of points. So one of the things that's happened within the last 10 years is that there's a safety standard called 9540, which is a UL standard that is now required in Canada for all battery systems to be tested to. The resi scale products are tested sort of a type spec at the factory, and so every battery they ship is certified, whereas most of the larger scale applications are field certified. But either way, they have to sort of go through this testing standard. And one of the tests that was added to the overall standard is 9540A, which is a fire propagation standard. And again, the original purpose was, well, if part of the battery catches fire, then we don't want the whole thing to set on fire or have this thermal runaway. So how can we make them safer? But again, all of that work and all of the development and all of the testing also makes these things more resilient to a fire that was caused by the structure or by a forest fire, like I said. So that's one thing, is sort of this certification approach has meant that all products sold in the Canadian market and interconnected with the grid now need to be certified. There's also a general trend of lithium ion batteries from one chemistry to another. I won't get into the exact detail, but there is effectively a expensive safe option and a lower cost, less safe option that is primarily used in vehicles. And the trend has been that LFP or lithium iron phosphate has come down in cost quite a bit, and in part tied to the safety testing, and in part based on the cost reduction, has really become the primary standard for stationary storage. So it used to be only at a small scale that was true. Now even the large scale BESS units are mostly all LFP for safety purposes. And it's just because it has a higher thermal stability. So it, just to be really plain about it, it takes a much higher temperature to cause the battery to catch fire if the fire source is external. And then there's a lower overall heat release if the failure occurs, which could cause less overall structural damage and or be able to be put out a little bit easier. On the residential scale, the way in which we try and tackle this is within the electrical code, you can only have 40 kilowatt hours in the home. That's kind of limiting the total heat release possible. And then we also spec through a variety of different standards in the electrical code, uh, locations for mounting. So you can't, of course, for example, put a residential battery in a bedroom, right? It has to be either on an exterior wall, or if it's inside the home, it's going to be not in a sleeping area and not below a sleeping area, for example, in a home. And so where we place it, the fact that it's third party certified, and then limiting the total size of the energy storage is the way in which we protect homes and then the people in those homes. And then commercial and utility scale, again, same certification, actually, 9540, just slightly different rules in the way that it's applied in the code. But then traditionally, it's just a lot easier to have these in full, storage or shipping containers. They're fire rated enclosures. They, at certain applications, need to have a certain fire rating in terms of, 1 hour or 2 hour burn, where if you had a forest fire around it, it's going to take a certain duration before it penetrates the actual enclosure it's in. And and again, like I said, the 9540 cert applies for these applications as well. It's typically done in the field because usually at a commercial or utility scale, it's a custom design of various components coming together, and that can only be field certified. Whereas again, the Resi products are more, we ship the box, it's set to be installed in a certain manner, and that's pre-certified from the factory. And then finally, I think as so if you're not familiar with that acronym, authorities having jurisdiction, or in other words, utilities or city permitting offices, anyone who's sort of saying where a battery is approved to be installed, the siting for where those batteries are going, particularly at commercial locations, is receiving more attention, probably rightfully so. And again, primarily that came from concern the battery itself would be the cause of the fire, but I think increasingly, you know, people can and should be considering how close they're put to fuel in terms of forest fire example, as an example. So anyway, this is overall the fire resilience. Again, a lot of it coming from battery standards that were developed to protect human safety, that actually help to protect the batteries themselves over time from external sources of fire. Somewhat related but different is now extreme heat and cold. So obviously, heat level below, having a fire nearby, but there's still, of course, areas that used to have a daytime high temperature annually of 30 degrees that now gets 35, or 35 in the Okanagan that gets 45 now, in some extreme cases. So these um, battery systems need to be able to handle that. They used to simply shut down at certain temperature set points. Increasingly, we're seeing advanced systems where they'll start limiting the max charge rate or discharge rate based on the temperature instead of just a hard shut off, which is great. It really allows you to kind of operate right up to the max limit of that device on the high end. And then in a lot of these storage systems, certainly all of the commercial scale, but on the Resi scale as well, heaters as well for low temperature. So sometimes, if there's a grid outage, the battery being able to operate in the lowest possible temperature is really important for human safety, right? If you can run just another hour or two of heat from the last state of charge in the battery, then it can really help human safety in a cold home, for example. Um, and I already mentioned this in the last case, but thermal runaway testing is required under the certification. And again, now I am talking about the risk of the battery itself being starting on fire based on the overall environment being too warm. So again, there's um, shutdown devices in place where the software will first shut it down. If the software is not shutting it down, and you have a thermal event at some part of the battery overall enclosure, then these things are tested so that that fire doesn't propagate within the enclosure. And then commercial is basically the same as everything I mentioned above, but also has HVAC systems in every container. That HVAC system will be designed for its application. So there's standardized solutions, but in general, they're going to look at, okay, is this thing going into Phoenix, Arizona, or is it going in Vancouver? There's going to be different HVAC requirements, of course, per container. So they have standard solutions, but they'll scale it up or down, both heating and cooling. And of course, that HVAC is being driven by the battery itself. And so you're sort of plugging in the battery, and then the whole storage container is operating as a unit. Often the inverters are inside that container in smaller applications. And then in the Tesla example I showed, they're external. But in all cases, the container itself is going to be managed from HVAC perspective to ensure maximum operating range, typically down to -30 or below, all the way up to above 40 Celsius. Okay, on floods, this one, is a little less, I would say, focused on, but certainly in the resi applications, just for general electrical devices, there's going to be electrical disconnects and breakers to avoid the risk of shock in the event that the water ingress into the home occurs. Mounting locations exist, so virtually every resi option that we have has wall mounts. I think it is important if you're in, certain areas, if you're close to the Bow River in Calgary, if you're in a floodplain in Richmond or wherever. I think wall mounts are important. If you're buying yourself 3 or 4 feet off the ground, I think you're massively reducing the risk that that battery is underwater. Primarily, water, though, is going to cause damage and not a major safety issue because of our electrical codes that exist. But I just wanted to mention there's, typically a wall mount, as I showed you in my example earlier on. At the commercial scale, so largely the two examples I showed you earlier of just a single container, or certainly the large, array of containers in the field, it's going to be a custom new foundation that's put in. And so again, if you were in a floodplain, relatively easy to just mount that, another few feet up. That's not going to solve all of the potential flood risk, but it can be a consideration that's easier on the commercial scale, because there typically is something new that's going in. I could be corrected on this. Please correct me in the Q&A if this is not true, but we've never seen a version that you can actually have water rising up the storage container itself. So it's typically going to be solved by increasing the foundation elevation and then just still putting a storage container style design on top of that. That's floods. Uh, Finally, under extreme winds, on the resident, so both resi and commercial, of course, a battery, in particular, a lithium-ion battery, has a high density, right? So a lot of weight, not a lot of area. That helps in extreme winds, of course. Um, some applications are outside, even at a resi level, and just mounted to the wall. But because they're so darn heavy, you're really physically, like you're attaching it into something really solid. You're attaching it to the studs through the external wall, through very I would say robust mounting techniques. And then because the amount of, wind exposure on that inverter or sorry, on the battery is relatively little and the weight is relatively large and therefore the mounting is very solid, I don't think it's a major risk on the wind front. Wiring is more of the risk typically, but in Canada, they're going to make sure that things are secured. So if you're using flexible conduit, for example, or rigid conduit or tech cable coming out of these batteries going into the inverter, again, on an outside application, they're going to still make sure everything is fastened down and protected against extreme winds. So we don't really see a big trend on this, even in the US where there's, tornadoes, hurricanes. This is typically not the issue. The structure itself is going to have much bigger issues if the battery is being ripped off the exterior wall. On the commercial and utility scale, same thing. These things are not only heavy already as batteries, then they put them in a metal storage container that's already very heavy. But of course, you can anchor that storage container down to the foundation should you wish for high winds or seismic conditions. So it's just kind of a run through. I know a lot of that is obvious. I'm hoping some of the industry specific context in terms of standards compliance and where the research has been focused is new. Now let's flip this around. And so I'll just finish on this slide, but I'll just say the top 4 ways in which batteries can actually help. So I covered where they can be exposed. How can they help? Primarily, they can support more solar. I showed this in the California example, but there's going to be a percentage in BC that we're nowhere near yet, but like California or Germany or South Australia, where we get to about 30% of solar penetration, meaning, 1 in 3 homes, let's say roughly, having solar, or 1 in 3 businesses, or both, beyond which the grid can become less stable if you don't have some way of charging the excess solar during the day and then shifting that to that peak that I described in the California example. So the first and foremost, in all ways in which batteries support higher hosting capacity for solar, we are helping with global climate change, right? And so even in BC, we're still importing some energy from the US market, and we're not having to build new systems that are hard on the climate if we can put in distributed solar systems. So first and foremost, batteries are helping increase solar hosting capacity. California, I already shared as the example. Um, the other way in which this helps is that we keep the power on when utilities need, dispatchable capacity. And so, again, during this peak demand example that I gave, during the in BC, it's typically still only during the winter period, but increasingly we will have summer peaks as well that need to be managed. And whether it's a summer peak or a winter peak, the utility dispatching battery storage or load reduction is going to keep the power on. And it's a simple example, but it's really relevant. So there's a reason why BC Hydro is increasingly investing in this peak saver program, or demand response program is another name for it. It's because they're going to see more and more extreme temperatures and be ready for that with getting the customers to participate with their dispatchable resources. So that's the second major way. Uh, the third is, backup power during outages. So the first two are about keeping the lights on. This next one is, okay, when the lights are off, are people going to be safe, right? And so primarily, we're talking about, critical load systems. Some people have life support machines at home. Some people have a medication fridge that they need to keep. And so I'm always thinking of, in our home, it's more the luxuries of life. And then we see real applications where people actually really do need this energy um, during an outage to keep safe and to keep healthy. And so those are more compelling applications of backup power. And I think the odds of power outages as climate changes will go up. And so if we're helping people by saying, well, when those occur, you're still going to be safe, that's overall being resilient to climate change over time. This historically made sense in off-grid. Now we're seeing it more and more in residential and grid-tied applications. And then commercial is another area that it applies. But in commercial, a lot of people that needed backup already have diesel generators as backup. But quite often there can be disruptions to machines in those cases. So even if it's a couple of seconds to start up the generator and an automatic startup and then the transfer switch cut over, there's a lot of commercial applications that would prefer to have an online standby device ready, even just for the first hour or two. So we're seeing commercial backup go up as an example as well. The large storms in 2021 in Texas is sort of the number one example of this, where people in ERCOT historically had really reliable power delivery, and then they have massive outages. The number of battery sales for this third main point after that huge outage really skyrocketed. And so the whole ERCOT grid is changing after that storm. Um, and finally, I just wanted to cover just briefly, again, it's sort of relevant in BC. A lot of off-grid communities are on diesel still. A lot of grid-tied homes have natural gas and electricity coming in. And so in an extreme weather scenario or seismic scenario, you may lose gas and not electricity, or gas and electricity. It's just another way to think about it. It's not only the electric system, but dual fuel applications, meaning that a home that is heated by either electricity through a heat pump or natural gas through a furnace can be using the heat pump during on battery backup, even though it goes through the battery pretty quickly. But you can still use electric generation of heat if you have a natural gas outage as well. And I just wanted to mention that briefly. So that's that, and happy to take questions. Aaron, I hope my duration was okay there, but that's the presentation. Open to questions.